All right, we're going to take a look to an introduction of integration. So we're going to go ahead and cut the margin all the way down and title your page The Integral Antiderivative. All right, so integration is used to find areas, volumes, central points, etc. But it is easiest to start with finding an area under the curve of a function that looks like this. Right, so we're just going to sketch like a function. So let's say we have a function like this. Integration would be to find the area underneath that curve. So what is the area under f of x? So let's call it f of x. Right, so there are a couple of ways that we could go about doing this. I'm going to draw 3 exact graphs that look like the graph we just drew. This is a listening check. Underline the title antiderivative. Alright, so there's something called slices. Like what it means is you take equal amounts of slices and make rectangles, because we know how to find the area of a rectangle. So if we know how to find the area of a rectangle, we can approximate the area of the curve by filling the curve with these equal sizes of rectangles. So fill the curve with equal sizes of rectangles. Alright, so calculate the function at a few points and add up the slices with change in x. Now the change in x is the difference right there, the base of each rectangle. That's the change in x. Alright, it's not a very accurate way of doing this when the change in x is so big. And let's take a look at why. So let me color in my rectangles orange. And again, remember the area of a rectangle we know is base times the height. In this case, that's the change in x, which is the base, times f of x, the value of x, the y function, the y value of x. So I have all these little pieces that are not accounted in the area, all that in purple, okay? But then also I have these other pieces that are over the curve, which means there's an overestimation. So right now, this isn't very accurate because I have, plus and minuses, all these little pieces. So to make this more accurate, I'm going to make smaller rectangles. So I'm going to make my change in x even smaller. So go ahead and make equal lines all the way through. And we're just making rectangles. Try and keep the change in x the same. Doesn't matter if it's not exactly as you can see. It's fine. It's just an approximation. So make my rectangles. This is a listening check. Put a box around change in x times f of x. Alright, so now let's look at what happens to my overs. So those are over my curves is in green. My under my curve is in purple. So you have all these that this area that I didn't find, and then the ones in green are overestimations. And then the orange would be all the areas of the rectangles that I found. So you can see that basically the smaller I make my rectangle, the more accurate I'm going to get, because you can see the extra shaded in is less. So the smaller my change in x, the better. So let's go ahead and write that down actually. So the smaller the change in x, the more accurate we get. There's less space between the rectangles and the curve, whether it's an over approximation or under approximation, less space. Definitely less than that first one we had. Alright, so the idea is basically as the slices get smaller and smaller, and they approach 0. So as the slices approach 0 in width, in other words, the change in x is 0. I'm going to label that dx actually. The answer approaches a true answer. This is a listening check. Color in 0. Color in the word 0 after approach. So we can now say dx to mean the change in x slices are approaching 0 in width. So from here on out, the x means the change in x slices are approaching 0 in width. But there's a shortcut. So imagine trying to find all these areas of these rectangles. It'll take forever. Okay, so there's a shortcut, and that shortcut is integration. So there's a shortcut to calculating the area of these infinitely small rectangles and then adding them up. So instead of calculating the area of these all these little rectangles and then adding them up, there is a shortcut. As a listening check, box the word add in. So antiderivative. Okay, so we're going to look at antiderivative is the reverse of finding the derivative. So antiderivative is also known as integration. It is the reverse of finding the derivative. So let's say we had x squared and you're told to find the derivative of x squared. Well, you guys know the derivative of x squared is what? You bring the power down and subtract 1 from the power, that's 2x. So that means if that's the derivative, the antiderivative is going backwards. If you're told to find the antiderivative of 2x, it will be x squared. So what is the integral of 2x? We're going to go over a couple of definitions. That is the symbol for integral. Then you have the function, and then you have the change in slices. So let me go ahead and label. That's a symbol for integration. It's like a long S, or stretched out S. And then 2x would be the function we want to integrate. And it's actually called an integrand. Integrand. And then dx is the slices along the x-axis approaching 0 in width. The listening check, color in slices along the x-axis. Now if you leave this out in any kind of work, you get a 0 automatically. Alright, so again, let's take a look at a few things. If you had x squared or x squared minus 2 or x squared plus 3 or x squared plus 4, when you take the derivative of all these functions, you're always going to get 2x. So look at it. So that's 2x and then the 4 goes away. That's 2x, and the minus 2 goes away. That's 2x and the plus 3 goes away. However, when you take the integration of, when you integrate 2x, you don't get that number back, right? So we have to account for that. Alright, so now there's like a little thing that you need to add. So the integration of 2x with respect to dx is equal to what you're going to get back, which is x squared plus some number. Because, and I don't know, I'm going to say plus c, because I don't know what that number is. It could be negative 2, it could be plus 3, it could be plus 4, whatever it is. So where c is a constant, so c is this number. So in integration, do not forget to put the plus c. It's actually something I always forget to do. But we're going to take a look at this. It's going to make a little bit more sense a little bit later on. This is just an introduction, just to kind of have you understand what integration is.